All right, so this video is actually going to be just a simple follow-up to a question that was requested, a problem that was requested for just review and to showcase a walkthrough on. And there was a recent tutoring session, several discussions leading up to this that made me realize I made a simple little mistake. And so I know this is for exam 3, and I'm trying to get this to y'all as fast as I can. So whenever you see this, right? But I often try and just communicate even outside of the video. So obviously I'm going to message you about this too. And this right here, it's actually just one little different thing. And I wanted to correct myself on what in this case will be the type of reaction. And first, excuse me, it's kind of early. So my like voice, not voice, but like, well, my throat is kind of like dry. So yeah, cold winter months. But anyways, you can see how given what we are starting with, the product side already shows this is just our table salt or just, salt has formed in ACL. So this is still showing a substitution occurring. Now, if you've seen the last video, I won't take down, it still has some great, discussion and review. It's just wrong on one little thing. I cover the fact that we have basically the type of nucleophile and even it's an aprotic solvent that would suggest SN2 reaction. However, it's the fact that this substrate, this compound has a tertiary alpha carbon at the side of where the chlorine will leave and the nucleophile will come in. So with that being said, before we get to that, I want to just clarify something. So even though, yes, a lot of the reactions are going to occur at some point, and thus you have this particular set of notes from Mass Organic Chemistry. It talks about how at some point, if you let it sit long enough, it's going to eventually undergo that type of reaction. It's just the rate at which it goes is what is going to, you can say, be unique about it because of the steric hindrance that possibly is there. We know that with tertiary substrates, the steric hindrance is massive. So here they show that the relative rate is very, very slim, almost to none, as if it won't ever happen. Well, our notes, so not just, like the book and everything, we have our table. We even observe, now this is in a specific time frame, but it is not going to occur immediately. Now that's clear from these notes, but there are a few other sources. This is, excuse me, hold on. So this is why several sources is good to look at instead of just one. And you try to see if it corroborates, right? This same source, though, talks about in a separate article or guide on deciding the type of reaction based on what sort of nucleophile you have, which this, of course, considers, you have a nucleophile here. It's a pretty strong one, right? Because it's coming from a salt. But regardless of that, the fact that you have a strong nucleophile in an aprotic solvent does not guarantee, of course, we know it doesn't guarantee that the reaction will occur in a shorter period of time. However, we're being told that tertiary alkyl halides never undergo SN2. So here's one source that says this. Another source, this is specifically from a book. It looks like from Kwantlen Polytechnic University. And so Liu, this book that is open sourced in LibreText website discusses the fact that, again, typically, if not all the time, tertiary substrates will not undergo SN2 reactions. And that is something that, if you watch the video again, right, I was actually, you can say, toggling in this area because when I looked at the problem again, that we're basically just going to redo here, I noticed that it was tertiary, right? And we know from our table that we've studied so many times that tertiary substrates favor SN1. They tend to undergo SN1 way more, if not always, SN2 than SN2, regardless of the presence of that strong nucleophile. So we have two other sources besides our text, right, that says that an SN2 will not occur. I'm trying to see where it was here. Well, here's the drawing. SN2 reaction rate of secondary and tertiary substrates decrease dramatically. Actually, this is funny. Actually, the tertiary substrates never go with SN2 reaction mechanism because the reaction rate is too slow. Now, my question, is experimentally, observationally, what does that mean in terms of time? Because the sentence before says that these two substrates, when the potential of an SN2 reaction can occur, the rate of that occurring decreases dramatically, right? So with that being said, it's not to say we're just going to say, no reaction. We probably can't, considering that with these the material here, the reagents or reactants, something did occur for us to get this salt, because that chlorine in this environment, right? In a beaker, you put these two things together, and then something else, you may have to set up a different way, but you get the point, right? You put these two things together in a system and allow it to undergo some reaction. Something did happen for that chlorine to not be on this compound, right? And is now an ionic bond with sodium. So iodine is on that compound. But now, after discussing all of that, the clarity here is that it underwent SN1. If you go to the slides for chapter 7, or you look at it in the book, same difference. It's going to be the same material. In 7.9, when trying to decide what mechanism it will undergo, SN1, SN2, E1, E2, right? What we see here is that they have the substrates on the row side and then the nucleophiles on the column side. Now, this is literally, now what I'm going to get into real quick is just how you approach using this. I do not like, this is just me being kind of picky now, because I'm like, man, I'm following, certain, rules tags. I'm trying to see what's the best way. It's a little unclear. I do not like how they have this stated. And I actually note this in the tutoring session recently. It says, once you determine which mechanism will be favored by the reagent, analyze the substrate. Now, that to me seems a little confusing, because if we are talking about, I'm going to assume now, considering the way that this talks, again, SN2 reaction rate for secondary, tertiary substrates decreases dramatically. Actually, the tertiary substrates never go with SN2 reaction because the reaction rate is too slow. It's just not as favorable for the tertiary. That's fair. Well, that means I really need to think of, the substrate first, because I can consider like what's the strong, given the strong nucleophile, what is the reaction that would go through, right? What sort of base you have, that will also determine it. So because we know that that chlorine is now with sodium, we can say that this is a substitution. So we're ultimately looking on the right side, but you would use like, okay, what sort of nucleophile and base up here to see, do we have a substitution elimination? All right. So past that point, of course, but I just don't like that they're basically kind of saying start with the nucleophile and then decide on the substrate. When you tend to read, this is such a picky note, but you tend to read the row first and then the column. So you will say, given my starting material, it has a tertiary substrate, boom. So I know I'm not looking through the rows, the possibilities of 1 and 2, right? And I think what's interesting here is that tertiary has a whole lot of different options. So now you do have to then focus on what type of nucleophile do you have. We really don't have a weak nucleophile. So considering our example or our practice problem, so our substrate is tertiary. It's an alkyl halide with a leaving group of a chlorine. And then the other thing is, right, our reagent shows our strong nucleophile. We have a aprotic solvent, acetone. Okay, so the possibilities is either we have an E2 or an SN1. Either an E2 or an SN1, which we know from our table. Again, if you go back to that, you actually see tertiary undergo E1 mechanism rather than E2 mechanism. Okay. So of course, given one of our products showing as a salt, NaCl, we know it's going to undergo SN1 in this case. Okay. And so let's go back here to our page, our problem. So that means with an SN1 reaction, So that's what you would state here, because I think it asked for, oh, it doesn't ask for it, but it asks for the mechanism. So you note to yourself, this is an SN1. That means the mechanism is going to go a lot different. So instead, well, let's just get it here. Instead of that nucleophilic attack occurring at the same time as the leaving group leaves first. And in this case, we get our intermediate. And that was being, we're just going to do this. Okay. It could be, actually, that's more likely how it will be drawn. Okay, so we get our carbocation. It's pretty stable given, what is around that carbon. And then our nucleophile is going to come in. I'm not going to draw in the box. I'll just say that's where it'll be placed, or in the picture. Okay. So instead of originally what I had before, when I was considering it being an SN2, right? It's SN1 reaction is going to show 2 steps here. And so we have this plus NaCl, and so this is what we get instead. Now, the rate determining step, now this SN1, is our intermediate. This also changes the way that we look at our energy diagram, the way that we would draw it. Now that we have an intermediate, there's going to be more change in that curved graph. Okay. And then the other thing they also wanted us to present is our rate law. Let me see how I drew it the first time. So yeah, so instead of it being second order, it's going to be first order. And I just drew there like my best attempt at drawing like the condensed version of this really large substrate or a compound. But yeah. So of the compound, that substrate, that is what's going to basically run the rate of that reaction. So it's less about the nucleophile when it's SN1. Okay. So let's look at, I think it'll be in here as well. Let's look at our energy diagram. So this is SN2. I want SN1. Here you go. So drawing from our study or our text here, SN1 reactions show a much more active or much more diverse, let me say, energy map than SN2. SN2 is a little bit simpler because it's just a concerted one-step type of reaction. With SN1, there's multiple steps. And so there's going to be more changes in our graph, right? And it's because of the fact that we're forming a carbocation, there's more changes in bond breaking and bond forming. So this is pretty much how our energy diagram map will look, right? It states too that the highest energy transition state is for the formation of the carbocation. It takes a lot of energy in, forming it and then, or rather breaking from it, but, actually holding it, right? So we start with our starting material. We lost the leaving group, so that energy is at a high point, the highest point. It dips a little bit at the point of the transitions or the intermediate, which is where our transition state is. And then we have our nucleophilic attack. It goes back up a little bit. And then as we are getting closer to our products, and the energy drops back down when we're forming those bonds. Okay, so proton transfer doesn't take a whole lot of energy, right? And this is the case if you have that last step at the end. So let me show an example of what that mechanism would look like, because this is something we did in our tutoring session. Actually, I think that's the same one, because I just drew it from the book. Oh, it's close. It's close. All right. So we have 1, 2, 3, 4, 5. We have this pentane with a methyl group and bromine group in its starting material. And ethanol is acting as the nucleophile here. So it comes in, undergoing SN1 reaction. Here is a tertiary once more. Undergoes SN1 reaction. So here's our intermediate. that then attracts the nucleophile to come in and attach itself, right? And so the last step, just so we get the final official product, right? The last step is this proton transfer. It's deprotonated by the ethanol group, the ethanol reagent. And then we're left with the final product here, which happens to be an ether, right? So this one. So this reaction has the same process. And so therefore its energy map is going to be very similar. The only thing we don't have though, of course, is the proton transfer because all we did is substituted one halogen for another. So this is just a nice sketch. It doesn't have to be perfect, but this is just a nice sketch of what our map would look like, what our energy will look like, our energy diagram, right? And so you can even state here, this is our carbocation intermediate, right? There's our reactant side, product side. Whoops. Product side. Oh, I thought it was in here. So if we go to our text, this is in chapter 6 as well. So reading energy diagrams. So I just want to get to the point where they talk about labeling the transition state. Actually, that's enough. So in our case, or in this case, we have two. Okay, so this is honestly enough, but this is showing the energy change in an SO1 reaction. Okay, so I wanted to do this video to correct on the mechanism type and just clarify what it would look like for this particular reaction. So this is going to be the case. I apologize if this was what I was leaning towards because I was thinking based on the solvent, or excuse me, based on the nucleophile. What's interesting this tells me is that this table is drawn out the way that it is for a reason. Okay. I've said it a few times too up to this point that certain ones are going to be what you can focus on as ways to determine. Because rate law, for example, rate law is not what you may use to determine if it's an S1 or SN2, for example. It is the result, what you would draw after you've determined if it's S1 and SN2. So based on that problem and going over the different sources again, what this tells me is substrate type tends to predominate the decision. And then you would look more closely at substrate and determining, but you will consider, of course, the nucleophilic strength in terms or for the substitution reaction, right? The solvent also plays a role, okay? And then the leaving group may be useful, but notice in that table, right? 7.9. Okay. I think it was like, oh, this is chapter 8. Okay, I'm actually much closer than I think. So 7.9 on analyzing and determining that table, this table right here, right? You would consider this table. I mentioned, it'd be good to probably remember this table as well, this chart. But what was I trying to say about this point? Yeah, so you will focus mostly on what type of solvent you have and what type of nucleophile or base you have, right? In terms of it being a base, is probably going to be leaning towards elimination. That's what that part means, just to clarify. Okay, notice how it tracks by saying if it's a strong base, right, it's going to be an elimination of some kind. If it's a weak base, it could be an E1. And if it's also a weak nucleophile, is definitely an E1, right? Considering what is the reagent. If that reagent, if it were to act as a nucleophile, is it weak or strong, right? I think this was also what was tripping me up personally about this problem. This is what I originally wrote, what I originally went with was an SN2. I figured because iodine is strong, right? It would be a strong nucleophile. And would it be a strong base? Possibly. Well, it could be considered. Could be considered a weak. Could be considered a weak conjugate base just because it can come from a strong acid. So I'm thinking of those terms. But yeah, I was considering with iodine, right? what type of strength does it have? So that's why I thought, oh, SN2. But notice we don't see in this chart SN2 for a tertiary. So that's what's interesting about the situation. Okay, so I'm going to just leave it there, given what I've presented. So this will be this will be the more probable situation, considering the type of substrate being tertiary, right? This is what would be the case. So, yeah, please consider this. Let me know if you still have questions. I am definitely going to be up and available for questions at the time of making this video. All right. And given the time of this video, I wish y'all all the best on this exam.